Hey, we'll be solving a matrix transpose problem. So I chose matrix transpose mainly because in the LeetGPU problems, vector addition is too easy. So there's not really a lot of opportunities for optimizations there. And on the other hand, the second problems, which is matrix multiplication, it is a bit simple for the naive implementation, but for optimizations, there's like a lot of things you can do. So it's a bit more complex. So I'll have to do multiple videos on it. So the starting of transpose would be like the sweet spot, in my opinion. So I'll be doing the naive implementation first, and then I'll basically show you guys how to do memory coalescing, and that's basically it. I won't be getting into other optimization techniques. I'm sure there are other methods for this that you can add on top. So I'll get to that later someday down the road. So to start things off, let's read the problem. So they want us to transpose a matrix. So for example, they give us a matrix of 32-bit floating point numbers. This is pretty standard. And the transpose of the matrix for a dimension row x columns would be columns x rows. This is all elementary too. So, but for people who don't remember it, I could just show you guys how to do it. So let's say there's a matrix of 1, 2, 3, 4. So the dimensions for this matrix would be 2 rows and 2 columns, so it would be 2x2. So the transpose for this matrix would be 1, 2, 3, 4. That's basically it. So basically all you're doing is making the rows into columns, and that's basically all you do. And so this would be a bit different for non-square matrix. So before it was a square matrix, so for example, if it's not a non-square matrix, it would be like 1, 2, and the transpose for this would be like this. So this is the transpose of the matrix. So this is something that you have to consider. So with this out of the way, I think it's pretty simple on how the naive implementation is implemented. So for example, if we have the coordinates, let me just write it 1, 3, 2, 4. So we have this matrix. So the coordinates for each element in the matrix would be 0, 0, 0, 1, 1, 0, and 1, 1. So the new coordinate for this one would become, so if we have I comma j for each coordinate, so the new one in the transpose would become j comma I. So it's just flipping the rows into columns and columns into rows. So the 1 would be the same. So the 2 would be 1 comma 0. So it will go here. So like this. And then the 3 would become 0 comma 1. So it will go here. And the 4 will remain the same because both of coordinates are the same. So it will be here. So we have a transpose here. So this is what we're going to do programmatically. And there are some quirks that you might use for CUDA. So to start things off, row major order is something important. So in memory, in C, the matrices are not stored like 1, 2, 3, 4. It's not stored like this. So how you access each coordinate is a bit different in C. So you use a formula called something like this. So basically row ID x columns. So this is basically number of columns, and we add the column ID. So this is basically like striding through. So I'll just show you guys how, like an example. I mean, this is kind of elementary for writing any CUDA code at all. I won't get into this in super detail, but I did explain it in my other videos. So so for example, this matrix would be stored in memory like this. So it would be like 1, 2, 3, and 4. So this is how it would be stored. So if we want the element, this one, so the row ID for this element would be 0. So 0x, the number of columns would be 2. So 0x2 would be 0. So 0 plus, and the column ID for 1 is just 0. So the ID of the element in the array is 0. So we get the element. So we want 2 now. So 2's row ID would be 0. So 0x columns is again 0. So I'll just clear it up. It's getting cluttered. So if you want 2 now, here it would be 0 comma 1. So 0x, the number of columns would be 2 plus the column ID for 2 is 1. So we get the ID 1. So you can basically see that this is how you access matrix indices in C with the row major order. So this is how you basically access it. So with this out of the way, I'll get to the code now for the naive implementation. So once that's done, I'll explain how the optimizations on top of this can be done, and then we'll implement that programmatically. Yeah, so we're in the LeetGPU site right now. It's pretty convenient to use. It's not an alternative to setting up CUDA locally because it's something you have to do if you're getting into GPU programming, but this is a pretty nice site for testing your skills. Anyways, so to start things off, I'll start with the implementation. So before we get started, we have to declare the block size. So they have a macro here, you have to define it yourself. So this can be arbitrary, but I'm going to go with 32, and there's kind of a reason that I chose it, but it won't really make sense if I explain why right now, but I will explain it when we do the optimization, hopefully. So anyways, we have defined the block size. So this is block size is basically like just a number of threads we're launching per block. So our thread is our block is square, so it's kind of like a square matrix 2x2, so it'll be like 32x32. So it's kind of overkill for square matrix, or like a really small square matrix, but it'll make sense. Anyways, we're gonna start with calculating the global index for row ID and column ID. So to start things off, I'll calculate the row ID. So this will be thread adx.y plus block adx.y start. Sorry, so this will be block div. So this can be block div or .y, or it could be block size. Both are pretty much the same because our 2D thread is squared, so it doesn't really matter how many threads there are per block. So anyways, so as for people who this formula doesn't really make sense to, this is pretty much how you calculate global index for the threads in the grid. So this basically tells us the threads position in the block. So if there are 10 threads in one block, this would tell us the position of it, and here the block ID would tell us the position of the block in the grid. So if this is block number 5, so this would be 5, and this is basically the number of threads per block. So when you multiply this, you basically get the number of threads that came before the current block. So when you add that with current thread ID, you basically get the global position of the thread in the entire grid. So this doesn't really get explained a lot, so I just had to get it in there, even if you know it already. So this is basically the same, but we do it for the x dimension. The order of picking x and y for the row ID and column ID also matters, but that also comes under memory coalescing and how we launch the block, so I won't really get into it. So just make it random for now in your head. It will make more sense that way. So we have row ID and column ID. So once we have this, we basically check our kernels our threads index. So we basically say column ID lesser than columns and row ID lesser than rows. So we're basically saying that do the transpose operation only if you're within our matrix. So if our thread isn't within the matrix, then it shouldn't do the transpose operation. So this is important because if our matrix is like just a 2x2 matrix and we're launching like 32x32 for each thread, then that's a bit of overkill. So we'll be doing like a lot of useless operations, and we'll also be writing memory to places that like out of the array. So that's also a problem. So for now, the if condition basically avoids us from doing any of that. And anyways, so with that out of the way, we have to, like I showed you before, we have to get the I comma j from our input matrix. So to get that for the row major order from the formula, so this would basically be just input matrix row ID star columns plus column ID. So this is basically how you get I comma j with row major order. So with this out of the way, we just have to transpose it and flip it to the output matrix. But there's something you have to do a bit different. So when you store it to the output matrix, you basically flip it around, because for the output matrix, when you transpose something, the columns of the previous matrix become the rows of the new matrix, and the rows of the previous matrix become the columns of the output matrix. So you have to flip it around. So this would basically become column ID x rows plus row ID. So yeah, this is basically the opposite of what we did, so to transpose it. So let's run it and see if our thing works. Yeah, let's pause. So yeah, this is really convenient to test your understanding. So I really suggest like working through the problems in LeetGPU if you're getting into GPU programming. So I'm gonna start. Let's see if it finishes up and passes all the test cases. As you can see, we did pass it, but we did really bad, because 7 milliseconds and 7.3 percentile. So this is really bad for a GPU, because the entire point of using GPUs for computation is speeding up performance, and this is super bad. We can do much better, as you can see from my previous submissions. So 88 is pretty damn good. So I'll show you guys how to get there, and yeah, so I'll get back to the drawing board so that I can explain how we can do the optimizations. Yeah, anyways, I'm back, so I'll be explaining memory coalescing and how to do it in CUDA. So we implemented our naive kernel, so we're going to look at the memory coalescing to optimize it so to improve our performance. So to start things off, to optimize it, we have to truly understand how CUDA schedules our kernel or parallel operations. So I'm going to assume that everyone knows what a kernel and a thread is. A kernel is basically kind of like a function that our threads execute in parallel. So how does it work? So for example, when we have this kernel, CUDA doesn't just automatically assign it to every single thread in our GPU, and it is kind of impossible because not every thread executes truly in parallel. So let's say we have like some thread here, it won't exactly run in parallel with this thread, because we don't have infinite threads in our GPU. It is pretty limited. So CUDA basically schedules like operations into warps. So a warp is kind of like a block, but it's entirely managed by CUDA, I believe. So a warp has 32 threads by default. So that's kind of why I declared 32 to make it easier. So a warp has 32 threads. So when you run this kernel for a warp, the CUDA will basically say run this kernel in these 32 threads in parallel. It won't run for the same data, but it will run in parallel for these 32 threads. So yeah, these threads in the warp are exactly what is truly parallel. So if you have a block or anything, it doesn't mean that every thread in the block or in the grid will execute truly in parallel. Only the threads in a warp can be truly parallel. So once you understand this, you have to understand that how our warps or the threads in the warp access our memory. So to understand it, I'll try to draw a diagram of our data. So let's say we have like an array of contiguous memory locations. So we have a bunch of data. So let's just pretend it's an array and we're doing some kernel operation on it. And we have a bunch of 4 threads. So these threads are all of the same warp. So the truly optimized way for our threads in a warp to do this would be to each of them taking the contiguous locations and working on it in parallel. So this would be really fast. But if if our memory is not coalesced, then this thread could work on this data, and this one can work on here, and this one can work here. So as you can see, this is much more messy and much slower because CUDA has to do much more memory transactions. So this is much slower. So this is exactly why our naive kernel isn't optimized. So I explained the integration behind it. So how does that translate to here? So our threads, if you remember how I explained the global index, so we have 2 dimensions. So our grid is was launched in 2 dimensions. We have x and y. So for all threads in x direction and y direction, it's in the x direction, it's more likely that they will be in a warp. So I have written 32 here, right? So these threads are more likely to be, these threads are more likely to be a part of the same warp. So when you launch a CUDA kernel, these would be executing in parallel. And so let's say you have a bunch of threads in the y direction like this. So let's say if you launch a kernel and the threads are working in parallel this way, they are not part of the same warp. So they would be much slower. So the right way to do memory coalescing is to make sure the threads in the x direction are of the same warp, are working on like contiguous memory locations, or like close data. So that's exactly what memory coalescing is. So to truly parallelize it, I will get into our kernel code. So alright, nice. So I'm back. So I'll be continuing with the memory coalescing explanation. So I basically explained that all threads in the x direction are more likely to be of the same warp, and on the y direction it would be memory coalesced. So we have to make sure that all our operations, that whatever we do on the array, so if these threads should be working on contiguous memory location. So what is contiguous? So if you know what contiguous is, basically, so if you have like an array of elements, so these elements that are next to each other, these are contiguous memory locations. So we have, if these threads are working parallel, they should work on parallel data. So this is basically what memory coalescing is. So we have to make sure all our operations are incremented in the x direction and they're working in parallel in that way. So we have our kernel here. So we do 2 operations on it. So first we get certain I, j, or y, x, or x, y from our input array or from our matrix, and then we are flipping the indices, and then we are storing it in like our j, I, or y, x in the output matrix. So we do 2 operations, read and write. So we have to make sure that every kernel is working on contiguous memory locations. So to truly do that, so let's look at let's see if this operation is memory coalesced, and then we'll look at this one. So we can look at here. So we have row ID. So row ID is thread ID x.y, block ID x.y. So this is in the y direction, and column ID is in the x direction. So it is more likely. So for threads in the y direction, they're basically the same. So if this is the first warp, so in the y direction this would be 0. So all threads would be 0. So let's do some examples. I'll walk through it. So we have 0. X. So now let's say we have a matrix of 3 columns. So this would be 3 plus column ID. So column ID would be so this would be x. So this would be 0. So here's 0. So for the first thread it'll be 0. So this one was 0, and next we work here. So this would be 0 to 0x3 plus 1. So this would be 1, and just like that we keep going. As you can see, we are working in parallel. So the read access is memory coalesced. And on the other hand, on the output matrix we're working on the column ID is x direction, and row ID is in the y direction. So when we are working in row major order, I'll demonstrate. So when it's in the y direction, we are incrementing with the row ID. So let's look at the warp. So the column ID for this one would be 0. X. Let's say rows are 2, and the row ID would be 0. So yeah. So this would be 0. So this thread would be working on the 0th location of our output matrix. So let's go to the next one. So this would be index of 1 in the x direction. So that would be column ID. So column ID is 1. So 1x2 plus 0. So this would be 2. And at the same time, this is 2. And this would be 2x2. So in the x direction, plus the row ID is 0. So this would be 4. Yeah. As you can see, so we are not working in contiguous memory location. So for each time, we are starting by the row length. So we're essentially working on different rows for each thread in like a warp. So this is extremely inefficient. So this would be starting by two rows. So as you can see, this would be much slower, like I showed you guys before with the analogy. And so to optimize this, we have to do a write operation and a read operation, both in a memory coalesced manner. But the problem is, we have to transpose our matrix, and the only way to transpose it is to flip the indices. So we can't really memory coalesce it with this way. So what if we could instead store this matrix data, so whatever we're working on locally, and then what if we flip the indices there, and then we write it back in our memory coalesced manner. So that's where shared memory comes in. So alright, so yeah, so the solution for our problem here is to use shared memory, like I told you guys. So shared memory is something that's on the GPU. So if you have a graphic card here, the shared memory would be on chip. So it would be much faster than accessing the global memory. So we're going to use this shared memory to store the data that we're going to transpose, and then we're going to transpose it within the shared memory, and then when we write it back, we'll just write it in our memory coalesced manner. So yeah, it won't really make sense right now. So as I code it and show you guys how it generally works, it will make much more sense, at least it for me. The LeetGPU side right now. So I'm gonna write the optimal solution. I haven't really walked through how the optimal solution works yet, because I think it will make much more sense after I code it and then explain how it works. So to start things off, we're gonna declare our shared memory. So it'll be something like this is how you declare shared memory. So it's kind of like global, but it'll be shared between each block. So in a block, it'll be shared. So here we call it a tile. So in each block would be working on a tile of data. So this would be block size, because the data will be shared between only the threads within a block. So this would be block size as well. We'll have +1 here to prevent band conflicts. I won't really get into it, but just pretend that it is something that we have to use. So yeah, so like before, I'm gonna calculate the global index. It's basically the same as what I did before, just the same formula. And at the same time, we have to calculate y. So I'm using x and y instead of row and column ID, so that it'll be easier to visualize like before, because all threads in a warp will be in the x direction, and at the same time, out of the warp will be in the y direction. So yeah, we have the thing here. So this is the data that we're going to store locally to transpose. So we have the if condition like before, where we're going to check the bounds for the data that we're going to work on. So this will be x will be rows and y will be columns. No, it will be rows. It's because of the row major order. I'll show you. So for starters, we're going to store it in the tile. So we'll just use the thread ID directly because it's only shared within the block. And we're gonna use input matrix. So we're gonna get it in the row major order in a coalesced manner like before. So it was coalesced, so it doesn't really matter. And we're gonna just do yx columns plus x. So I used y for rows here because in the y direction we want it to be the same. So yeah. And at the same time, so now we did this, and next we have to store it in a memory coalesced manner. To do that, we need to new global index for writing it back. So we calculate it, and I'll explain why. So int x. So this will be calculated differently. So the thread ID will be the same in the x direction, but we will change the block ID. Yeah, so I'll explain why it works. I'll get back to the main thing. I'm gonna clear this so I can explain it. So yeah, so we have our shared memory. So I'll make a matrix. So imagine this is our matrix, and yeah, it's just really bad right now. Let's just pretend that it's a matrix that we're working on. So each block in the matrix is a tile that we're working on. So let's say we have our block or something is working on this tile. So this tile would have data 1, 2, 3, 4. So what we are doing by transposing is to transpose, we have to flip the data to indices. So this is what we're going to do with the tile. So this will become 3, 4. And then we can't just leave a tile here because that's not really what transpose is. So even if we have 1, 2, and 3, 4, we have to move the entire tile to the transpose location. So the tile has to move here. So it should become 1, 2, 3, 4 here. So to move it, we're going to flip the global index calculation. So that's exactly why the index calculation is a bit different. And saving it is pretty straightforward. So I don't think a visual explanation is necessary. I'm back on the LeetGPU side right now, so I'm going to get back to writing the code. So this would be same. You just calculate the bounds for our new indices. So this would be new x. So basically, when we transpose something, the rows and columns would flip, right? So if we have our row x columns, when we flip it, it'll become columns x rows. So to represent this, I'll make new x columns to make it simpler to visualize. So this would be rows, and new rows would be columns. So this is pretty simple. And here, the new x, we'll continue using it for new rows because we want it to be memory coalesced. And at the same time, new y will continue to be. I flipped it around again. We're going to continue using it for columns, and we're going to use it for rows. We check the bounds for the new columns and new rows. And once we did this, we just write it back in a memory coalesced manner. So this will be just new y like before, x new columns, and we just increment it by our new x. So this should write it back in a memory coalesced manner. And just to reiterate, it doesn't matter here that we're flipping it around, because in memory, in row major order, it's just like one array. So the stride for the row, it doesn't really matter because it's still contiguous. So once you do that, you just flip the tile. So this would be the IDX. So we're going to transpose within the tile too. So this will become x, and this will become y. Yeah. When I run it, it should hopefully work. Let's see. Oh, oops, I messed up the calculation. So I just used muscle memory to type it out. So I'll just send this to block it. Yes, I'll just do that. And once you do this, there's also something that I forgot. So this would be, I think, sync threads, because we wanted threads to finish this out at the same time before they move on to this. So this is mainly to prevent race conditions and weird shit like that. So I'll run it again, and it should work this time, hopefully. As you can see, passed, so we'll submit it, and it should compile. Oh, 87, that's pretty good. I'm going to stop the optimizations here. So I think there can be more things done. This can be done more efficiently too, I believe. And there's also a technique called thread coercing. I'm not sure how to pronounce it, but yeah, once I learn it, I'll make a video on it, hopefully.